we report on experiments on electrostatic instabilities, turbulence, and interaction of this turbulence with the fast ions in what we call a simple magnetized plasma. It's a toroidal device I'll describe. I'll do that on behalf of the CRPP basic plasma physics group, whose people are listed here. There are also a number of old and new collaborators here, including Stefan Brunner from our theory group and Barrett Rogers, who's on the back there, who helped with the theory. Now here is a tribute to a previous speaker. Now we're looking at the intermittent transport in edge plasma, which is a very important basic problem for fusion. Of course, it determines interaction of the plasma with the wall. Might be one of the showstoppers for fusion, the efficiency of the diverter, and in turn the confinement, even in the core. And these intermittent events are observed in a number of devices and in a number of configurations, going from a linear device, which we just heard about, LAPD, to actual tokamaks. This is an STX. This is an imaging of the edge of an STX. You see all of these events. And this is a time trace of a probe signal from our own tokamak TCV in Lausanne. You see intermittency there too. So our idea was to study this in a configuration that's sort of in between a linear device and a tokamak in terms of complexity, which is toroidal, so it has still open field lines, but it has grad B and curvature effects. So this, we believe, is a very good setup for model validation, and this will be one of the important aspects that we're trying to address. So let me say a few words about the machine, and then we'll try to make a sort of a complete story of one piece of our studies to try and convince you that we can contribute to the validation of the theory for this kind of effects. So we make this a toroidal device. Simple magnetized plasma is a term that refers to a situation in which you have a mostly toroidal magnetic field on which you put a small vertical field. So you have helical field lines around the torus like this. We make the plasma using ECRH at 2.45 gigahertz, relatively small power, hundreds of watts, so up to a few kilowatts. We have no plasma current. And of course, in plasmas that are of the order of 10 eV for electron temperature and 10 to 16 for density, you can put probes and also the diagnostics inside and cover the whole cross section, which is a key point here. And as I said before, we have pressure gradients, obviously, and grad B and curvature effects. So we believe we can perform a complete characterization of turbulence in conditions that are relevant to the tokamak strip of layer. This is a picture of the target plasma. The white contours are the time average, is the time average density profile, and you will see it's a very turbulent plasma. These are just a sequence of frames on the plasma. You can also see already that you have structures that detach from the region of the plasma where the production takes place, the ionization takes place, to the low field side. This is a hydrogen plasma. We're not going into the details, but we have a slab-like average profile, which is characterized also by a fairly strongly sheared E cross B velocity we can also measure. These measurements are taken by a number of tips, Langmuir probe tips, across the cross-section, about 100 probes. And the other point I want to make here is that, as I said before, we have a region where the plasma is formed. That's where the resonances are with the EC waves, both the EC resonance itself and the Abbe hybrid resonance, which is where most of the ionization occurs, and a region where there is no plasma except if there is transport, which we refer to as source-free or blob region.
Is the resolution of the blobs we see likely physical, or is it the number of probes that's making those sizes?
No, this is still physical, and is not much bigger than the resolution of the probes themselves in this case. But I'll comment on that later. And it's also a motivation for a new set of diagnostics we are installing, which is actually fast cameras. So again, to discuss about these two regions, because I think they are important and also akin to what happens in tokamak. This is a profile, a 2D profile of the skewness of the ion saturation current signals, or say density. There is a region, the source region, where this skewness is close to zero or negative but small. And then the region where we have blobs, where the skewness is positive and relatively large. So there is a transition. That transition is exactly between the source and the blob region. That transition is very similar to what's observed in tokamaks, corresponding to the last closed flux surface. This is an example from Jose Boedo. That's the skewness of delta n over n. You go from negative to positive pretty much across the last closed flux surface. So let's look on the left, which means the mode region. That's where we have a quasi-coherent set of oscillations. Spectrum is dominated by a coherent feature. In this case, it's a 4 kHz feature. And the PDF of the fluctuation is a double hump PDF, which means you have strong quasi-sinusoidal oscillations. Let's look on the other side. That's the blob region. It's really a completely different characteristics in terms of fluctuation. You have intermittence, so you have nothing and then an event coming. The power spectrum, of course, then is not dominated by a single line, but is fairly broad. And the PDF is skewed, as shown here, positively.
What is it for developments, the
Fairly high, fairly high. So you go from a few percent here to almost 90%. That's controlled in a way by the source that we impose, by the strength of the source we impose by our ECRH. So let's look, before we try and understand what these modes are, let's look at what the statistical properties are of these modes, of these fluctuations rather, I should say. I call this universality because we look at a fairly large number of signals, more than 10,000 time traces, in different gases, in different configuration in terms of magnetic field, and in different ranges of the fluctuation amplitude, almost up to 100%. And here we put the RMS on the vertical axis as a function of kurtosis and skewness, third and fourth order moments of the PDF. And we see, particularly if we look at the projection here, which might not be so visible in this 3D plot, but it's more visible here, we see there is a unique relation between kurtosis and skewness, and it's always the same. Not only is it always quadratic, but it has always the same coefficient. So we believe this is an aspect of a universal phenomenon. We try to fit the distribution function, the probability distribution function, to different kinds of known distributions, analytical distributions, and the best one is the beta distribution. It's sort of a combination of two gammas, allowing for negative skewness. Now we look at other fluctuations from tokamaks. This is an example of TCV. We look at sum of jet, and they all fall on the same curve. So this is a kind of interesting, I believe, observation. Whether it's complete triviality or it's an intrinsic aspect of these interchange modes is sort of still an open question. But I think the fact that the coefficients are always the same is fairly important. And we've seen that in the literature this is common to a variety of fluctuation phenomena when you have strong convection, for example, surface waves in ocean, and I think also X-ray oscillations in accretion disks. But I don't know if some of the experts may confirm that from the audience here. So this is sort of the introduction of what we see without doing anything, any interpretation to these fluctuations. Now, let's look at this story that I try to complete today. These are the questions I'd like to address. What kind of modes are responsible for the turbulence? How are the macroscopic structures or blobs generated? What's the mechanism behind their formation? And once they form, how do they propagate? How do we control their dynamics, or can we control their dynamics? Now, once they're there, then let's see what the consequences are of these blobs. And I took two examples for today, the plasma flow and rotation, with some open questions that I hope will be of interest to you. And also, similar to what's been done on LAPD, we look at the effects of these blobs on the transport of non-thermal plasma particles, in particular fast ions we inject with a similar source. I'll discuss that without alpha n waves, nevertheless. And finally, one point that I'm quite keen in discussing with you is how can these results be used to quantitatively validate theoretical model, not just say qualitatively, okay, there is some sort of agreement. How do we quantify such agreement? That would be my last point. So first, I do kind of the homework of trying to identify what the modes are that are responsible for the turbulence. Now, it's true that it's very boring to do it, but that's what you have graduate students for. And one first graduate student on topics did that, and she was very patient. It's a little easier for us because, of course, you have a toroidal device. You can look at the propagation toroidally, you can have many turns, so you just have to be very careful where you put your probes, and it's a pain to align. But we believe we can do it. We have done it, and so you get the K parallel versus F spectrum, so the parallel dispersion relation, if you like. Perpendicular, the same thing, is two-point correlation, but it's much easier technically. So what do we see? We see two distinct regimes in this set of conditions I'm reporting today. This is the K vertical, K perp, if you like, K vertical wave number, as a function of 1 over the vertical field magnitude, which is then basically the number of turns that the field line has inside the vessel. It's kind of nice to put in this simple, in terms of a simple number like that. So we see a first group of points in which we see a almost linear dependence of K perp upon the number of turns, so upon 1 over b, z, and a 0 K parallel within our errors, of course. But we also see a second group of points. These are condensed from many points, in fact, where K parallel is non-zero, clearly measurable and clearly non-zero, and where you have no dependence of K perp upon the vertical field, so upon the pitch of the field lines. So we look at the interpretation of these points from theory. So we have a fairly collisional plasma, so we use Brzezinski, small number radius, and of course very small beta, and frequencies well below omega ci. So we can use the electrostatic drift reduced Brzezinski, three equations, the density, vorticity, and temperature. And so we could put basically the theory lines upon this experimental plot, and we see that we have two distinct regimes. The first regime being the ideal interchange regime, K parallel practically equals to 0. Vertical wavelength basically dictated by the separation between the return points of the same field line. And the second regime, where the vertical wavelength basically corresponds to the largest available scale that you have. And this is a so-called resistive interchange mode. K toroidal is 0, by K parallel is not. And that's clearly measured. So I think we know what the waves are, which is, I think, is a very important starting point. In some other cases, we have, especially on the high field side, we have drift waves, etc. But we will concentrate on the rest of the talk on these pure interchange modes, which have K parallel of order 0, actually identical equal to 0. This is a 3D simulation for n equals 2, so a situation dominated by K parallel equals 0 modes. Of course, this is nonlinear evolution, and you see from this simulation that you have regions of plasma that are detached from the source region, and they are expelled out towards the low field side. So this is sort of a prediction from theory, in a sense, that you have blobs generated there, and they propagate to the low field side. So let's look at these blobs experimentally. How do they form? Now, to do that, it's also fairly time-consuming experimentally, because we didn't want to measure the floating potential. We wanted to measure the plasma potential. Yeah, sorry?
On the simulation you just showed, that's a phi contours. And is there any...
That's right.
Is there any issue in measuring phi versus density, or in the theory, is the density tracking phi closely? How does all that play out in the system?
What do you mean in measuring phi versus density?
Well, typically you guys tell us that you measure density fluctuations rather than electrostatic potential directly.
No, that's what I was saying. In fact, for the experimental part here, we went through a lot of trouble to try and measure both potential fluctuation and density fluctuation, and not just floating potential fluctuation, which is what most people do because it's the easiest thing, but via conditional sampling, also plasma potential fluctuation. So in other words, you get rid of the assumptions on the temperature fluctuations, which is very direct.
Okay.
So it takes a lot of discharges. Now, we have much longer discharges than LAPD, but we can do also maybe 800 discharges a day over a few seconds. And in this case, we use conditional sampling, basically to have alarming characteristics done so many times that you can look at each point of the characteristic and as a function of the events that happen in your plasma, the position of your reference probe. Which means you can reconstruct really the density and not just ISAT, and again the potential the plasma potential fluctuation. So this is a movie, a conditional sample movie of the density perturbation associated with one trigger point, which is here. This is the time trace of the density at that trigger point. 0 is when something happens at that point, so that's the event which constitutes our reference. And that the event there is when a blob passes by. But of course, if you didn't have the 2D reconstruction, you could have some sort of event which is not a structure, but we do have the 2D reconstruction, so we know that the event is a blob. Now look again, so now it's passed. Now this is the interchange mode. Okay, we start over. This is interchange wave crest, if you like. What happens now is the wave crest elongates. I think this is the one, yeah. Then there's shear flow coming here, and shear flow breaks it apart and makes this bubble, which is then sheared off, and that becomes a blob. That becomes a separated structure. These coherent structures that move with V cross B, but there's shear in E cross B again, which shears them off. How long does it take for them to be sheared off? Well, it takes about 100 microseconds. You can even see here, this is 100 microsecond time scale. And if you compare with a simple estimated shearing time from Biglari et al., putting the numbers that correspond to these quantities, which we measure directly, you can get an estimate, and that's really in the same ballpark. I don't mean it's exactly 100 microseconds, but it's really the same order of magnitude. So I think we therefore know the mechanism of formation of these blobs, and we know that the energy is transferred from the shear flow to the blobs. Now with these 2D pictures, you can really look at what happens. Now they're formed. We know how they're formed. We know what the instabilities are in the background, if you like. Let's forget all of that. Let's look at how they move once they form. So we go in a region where there's nothing else but blobs, and we look at the structures that are in those regions by identifying a structure as a region of plasma in which the perturbation exceeds some sort of threshold value that we fix, typically 1 or 1.5, the standard variation over the whole time trace. Then we intersect, we create a contour where the density perturbation intersects this threshold condition, if you like. And that contour defines your structure. So once you have the contour, frame by frame, you have your structure frame by frame. So you have the center of gravity of the structure, you have the elongation, the shape, how much mass there is inside, and so on. So you have all of that 250 times, 250,000 times a second. So you have immense amount of data on these structures. Then you can define observables for these structures. We have, 15 observables. Some of them we never use really, like aspect ratio and so on and so forth. But they're there particularly for comparing with theory. So they can be treated as so many. They can be treated statistically, but you can also follow individual blobs throughout their lifetime, if you like. This is the resolution that we have in our triangular mesh. So in particular, what we wanted to do was to assess the motion of these filament and blobs in terms of their radial velocity and in terms of the vertical size, which is normally what's considered in a tokamak strip-off layer or edge physics as an important parameter. Now we wanted to even further simplify our own geometry by inserting a limiter. Now a limiter is a big name, it's just a plate of metal which is perpendicular to the field lines, so you can set a very simple boundary condition, which is, all field lines are pretty much 90 degrees impinging on this limiter. It also means that you have constant connection length. You don't have this complication of varying connection length and so on. So it's a very simple setup. We have seen how we identify the blobs, and it's very easy to measure their vertical size and to measure their velocity because we track them frame by frame.
Should we be thinking blob steel is conducting or insulating?
It's conducting. It's conducting, of course. Yeah.
Enough? Yeah, okay.
Yeah. And density. So we can statistically look at many blobs and look at the, if you like, the joint probability between the size, vertical size in this case, and the radial velocity of these blobs. Now, we took the existing models and we look at the equation where the models were taken from, and we noticed that actually some of the terms in the equation, despite being very simple, were not accounted for. So we tried to account for all of them. Now, this is a picture from Krasheninnikov. It is usual picture. You have charge separation due to curvature inside the blob, and of course that has an electric field which drives the blob outwards. This is typical mechanism for the blob drive once the blob is formed. How do you damp this velocity? Well, of course, you have to provide a current that short circuits such charge separation. And the current can be parallel current for the sheath if you are connected to a metallic object. It can be polarization current across, or collision-induced current. In this case, we take into account ion-neutral collisions. Now we put the estimates for these terms for the interchange wave-dominated regime, and we find that everything can be cast in terms of a simple relationship between the normalized blob velocity and the normalized blob vertical size. Again, these two elements are the ones that are considered for edge fusion plasmas. And of course, you have the delta N over N term there. So we measure all of this. These are the usual normalizations that Krasheninnikov and et al. Used.
What is the term on the left? You mentioned there's some new terms.
Excuse me?
What is the term on the left? Sign. Where is it?
This is the drive. That's your charge separation due to curvature. This is the polarization. This is a sheath, and this is collisional term. So these are the same color. So if you do the normalization, this term becomes 1. So we looked at the statistics of all the blobs we could generate. We did it for one gas, and we were not happy enough because we had kind of a cloud of points. This is the limit of our resolution, by the way, at present, or at that time, in fact. And we said, how do we vary this? Well, we varied that cloud by taking different gases. Sizes turned out to be fairly similar, but the velocities were not similar. A and B, in the normalization factor, you have the mass, so you can cover quite a range, which is impossible to do in tokamak edges, absolutely impossible. So we did, and we put all of this data. This might be thousands of points on clouds for each gas, and on V versus A normalized plot, where you have the two lines that were used before in the literature, the parallel current damping and the damping due to polarization currents. In the two limits, these would dominate a very small or very large blob, but most of the blobs are actually in between. If you don't put the generalized model, in other words, the model that has all the terms, actually it's completely wrong. But if you do, it's fairly good agreement. So I think we now have a nice way of describing the blob dynamics once it's formed. And one step we can take is to try and influence that. Now the idea came, I think, originally from Cohen and Rutov, say the parallel electron currents are one of these elements that short-circuit the separation inside the blob, that therefore should damp the blob motion, depends on the angle between the field lines and your wall. So why don't we build something in which you can vary that angle? So we built a limiter with tiltable plates to try and control an angle. That's what it looks like inside the machine. So it's many blades, and you can turn it from outside. It's a nice Swiss watch-like mechanism, extremely complicated. And we vary that. We can achieve fairly small angle, fairly big angle, but the result is fairly clear so far, and fairly clearly negative. So there is no influence. So maybe it's something specific to our setup, I don't know. We need to check that, but I think it's an important point that prediction is really completely not followed by the data. So let's look at the consequences of these blobs. I said I've chosen two examples. One I think is particularly interesting for this audience, also based on the discussion we had yesterday. What do the blobs do to the plasma flow, or to the plasma rotation? Here's what they do. Now here's a blob that comes. It's a function of time. These are conditional sample signals. Density perturbation is a function of time. So the probe is there at some point close to the edge of the plasma, and a peak in this curve means that the blob is coming. That's where the blob is, reaching the probe. What happens to the toroidal velocity, like the plasma rotation? Well, it gets affected by that blob. These are two cases for different signs of the vertical field. It's just two different configurations. And it gets instantaneously affected. So the blob does carry a perturbation of angular momentum, if you like. Let's look at that in a time-resolved way, but in a profile, and you see that there is sort of a no-local structure. This is the variation in the toroidal rotation of the plasma as a function of time, when 0 is the time when the blob gets to the reference probe. So there is a structure there. This is the density structure in black contours. It's kind of a non-trivial relationship. So let's look at something that, again, cannot be done in tokamaks, that is at the 2D profile of this event. This is a 2D profile that we have already seen of the density or the ion saturation current perturbation in this case. Top and bottom are two different times. This is before the blob, and this is exactly where the blob gets there. We've seen it before. And this is the 2D profile of the Mach number perturbation. And you see there is structure there. You see there is a phase between the density perturbation or the ISAT perturbation and the Mach number perturbation, which is in this case pi over 2. And interesting, that phase is carried along by the blob throughout its life. So in other words, if you create a blob which is exactly 90 degrees out of phase compared to a blob in the velocity compared to the blob in density, that phase relationship is carried with the blob until it dies. That's a density blob for reference here. And that is, if you like, the toroidal velocity blob. The other case, which is a different sign of a vertical field that has a monopolar rather than dipolar structure. But the bottom line is that these structures are created where the blob forms, and then they're carried along by the blob as it moves. It also underlines, as I said before, that you absolutely need 2D coverage, some sort of no local effect, in order to understand anything about this rotation business and this intermittency in the rotation. This I might just quickly remind something we've done recently, trying to compare the different terms, Reynolds stress, convective term, and so-called nonlinear term, showing that in this case, it is not the Reynolds stress that was dominant. It was, in fact, pretty much negligible. It's the convective term, again, these blobs carrying momentum with them, that seems to be the dominant effect. This is something that I like as a simple experimentalist, and that is that this perturbation in the blob, in toroidal velocity, is proportional, both when it's positive and when it's negative, to the size of the blob, which we determine by the level that we use to define the blob in our sampling technique. So something that's really proportional to the size. So really leads me to conclude that the toroidal velocity blobs or holes, depending on the sign, are associated with density blobs. That's something that I think is absolutely uncontroversial. And it's something that can provide a nice test bed for theory for this business of the toroidal velocity. Now I want to make somewhat the connection between our work and what's been shown by Troy before. I look now at the effect of these blobs, this turbulence in the edge, to the transport of non-thermal plasma particles, these fast times that we inject. This is a kind of a work in progress, and I don't pretend I have a conclusive results, but I think it's nice that you get a feel of what we can do on this kind of device. So what we do is to inject lithium ions from a small lithium emitter, which is much smaller than the one in LAPD. It's a miniaturized version, if you like. We're developing collaboration with them, or with Heinrich and his group. Once you emit them, you accelerate them, so you control the energy up to 1 keV. We use less energy. We use of the order 100 eV, which is of course very superthermal in our case. Now, once the beam is ejected, which is done in a fairly colorimetric way, then it's detected by a gradient energy analyzer, which has a front end which sees the beam, and then the back end which just seeing the noise. It's just to improve the signal to noise ratio. Both of them are mounted on movable systems, so we don't move necessarily discharge by discharge. We can also move all of this within one discharge, and so we can cover the whole cross section. So we can inject in a mode region, or we can inject in a blob region and see the effect of the two regions. In what we see today, I will inject in the blob region. And after about 25 centimeters, we look at the fast ions. Where have they been? Have they spread? Have they changed energy, and so on? In this case, I'll use 300 eV ions. So this is a spreading. Now you might say, okay, it's fairly small. Indeed, it is fairly small. The vertical spreading is due to the source properties, so it's not really that interesting. The radial spreading is due to the interaction with plasma. So that's the interesting part. So it's small but systematic. We observe it all the time, and it's only there in the presence of plasma. This is without plasma, and this is with plasma. Without plasma, with all the magnetic fields and so on. But with plasma, you see the plasma interacts with the fast ions and it spreads them. Now, because it's small and because we only have one point so far, one spatial point, we need to look at the theoretical approach to really understand if it's reasonable to think that it comes from turbulence. So here it is, the 2D simulation, again from Paula and Barrett. What we do is to inject the fast ions with exact source characteristics as we have in the experiment, and I don't know if you can see there's a tracer here, and look what happens to them as they go along the machine in the presence of the electrostatic turbulent field modeled by the 2D simulation. In this case, I think we multiplied the field by a factor of 2 to make it of the same amplitude as we measure. And I think you do something very similar, don't you?
Is the size of that circle representative of the gyre radius of this particle?
Yeah.
So a lot of the effects people worry about with fast ion transport is when the size of the orbit of the particle is much larger than the eddies. Can you get to that limit?
Yes, we can vary the energy. We can vary the energy. We can also vary something that's interesting for fusion, of course, is the energy over the temperature, because that's a key element. So if you do that simulation and you see something fairly similar to what's seen experimentally, which makes me believe that indeed this radial broadening is due to turbulence. It's not conclusive entirely yet, because what we want to do is to really look at the mechanism step by step. How is this broadening taking place? Is it diffusive? Is it super diffusive? Is it ballistic? What is it? So before I look at the kind of into the future, I'd like to discuss with you how can these results be used to validate theoretical models, to quantitatively compare. So here's one is our approach. Again, it's a first kind of approach, and I'd be super happy to hear feedback on this. First thing, of course, you have to define observables. We have observables from experiment and from theory. Then we define what's called the primacy hierarchy, a little bit like what Paul Terry and Martin Greenwald have done recently in the US. Classifying, if you like, the variables in terms of how many assumptions you need to get them from theory and from the experiment. For example, ISAT is something you measure directly, so it's 0th level. The temperature in the model is something that is one of your independent variables, so it's 0th level. But if you go to the model and you try to get ISAT from the model, you have to do something. You have to make some assumptions, so it becomes 1st level. Density in the experiment, you have to make assumptions that become 1st level, and so on and so forth. You go 2nd, 3rd level, and so on. So how do we measure how good is the agreement with a given model? So we try to really condense that into a single parameter, which I don't have a nice name for, maybe a degree of agreement or something like that. I call chi for the moment, which is defined in the following way in our proposal, if you like. It's a sum over the observables of 3 terms, of the product of 3 terms. First term is basically the one that defines whether or not you agree, which means whether or not you're inside the error bar between experiment and theory. Now, this may be sort of binary. We had a kind of a smooth curve to go from 0 to 1, if you like, agreement versus disagreement. Second point is how much weight do you give to that particular comparison for that particular observable? And we calculate that in terms of the features of that observable, how much error characterize that observable, both experimentally and theoretically.
Excuse me, is R like a correlation coefficient? And if it is
not really.
Anti-correlated?
Not really. Is R tells you, okay, are you inside the error bar or not? If you're inside your is 0 if your outside is 1. So inside is good, outside is bad. Now what we did is to take a smooth curve, I think it's hyperbolic tangent that we took, whose middle point is a 1.5 sigma or something like that. And we played with that a little bit. It doesn't really affect the result that much, but it's a matter of debate, of course. And HI, so H for each observable, is of course the hierarchy level for that observable, which is 1 over 1 plus the hierarchy level from experiment plus the hierarchy level from model. So this measures how indirect is the information carried by that particular observable. So let's try to apply this to a number of cases, in fact. So this is an example of the output of the 3D model from Paolo and the experiment. This is just a radial profile of density, so nothing special in there, but it's one of the starting points. So we use the 2D and the 3D fluid model and try to compare them, which we applied to 4 different configurations in which we vary the vertical field, which is represented again in terms of the number of turns that the field line makes inside the vessel. And we took, in this case, how many? 11 observables, all of them with HI of 0.5. But each observable, at least many of them, are profiles, so there's much more than 11 points. These are, and of course, they are also time traces. So the density profile, temperature profile, potential profile, plasma potential profile, skewness profile, kurtosis profile of fluctuations, of ISAT, I believe, fluctuations on density and the saturation current. We also took the PDF or the fluctuations as an observable, the power spectral density, the spectrum in KZ, both measured and calculated, and the K-toroidal spectrum at the location of the maximum mode amplitude. So these second class of points are just points at one particular location. So here's the result of this first attempt. This is this chi global parameter, degree of agreement, if you like, as a function of the number n, which is the parameter that characterizes the difference between these experimental runs for the two models, the 2D model and the 3D model. And of course, if you're close to 1 within the error bar, if you like, or close to 0 means respectively complete disagreement, which is bad, or perfect agreement, which is perfect. Now, if you start with low n, you're in a situation in which everything is sort of should be described well by the 2D model, because K parallel is 0 and it's slab light and so on and so forth. And it is. There is no significant difference between the 2D and the 3D model. So you can say, okay, I agree with the 2D and the 2D model. Or actually, the other way around. They agree with my data. But if you increase n, you go less and less slab-like, if you like, and you get the components with K parallel different from 0. I think it's a nice example that you say, okay, 2D is hopeless. It's not going to work. Quantitatively measured this way, the agreement is just too bad. I cannot hope to describe the experiment with a 2D model. I do hope, and I do describe the experiment with a 3D model in this case. Now, whether this has to be 0.4, 0.3, or 0.2, this is a kind of a matter of exact definition how we do it, and it's something we still have to improve probably, but at least the difference between the model, I think, can be quantified pretty well in this way.
Could you explain, I thought HI was going to have a maximum of a third from your previous slide, but it seems to be as large as a half.
No, you can have a hierarchy level of 0.
There's zeros.
There's 0, yeah. 0 means no assumption, something direct. So let me summarize and say a few words about what we're going to do next. I don't summarize all the results. I just say that I hope I convince you that these results from the simple plasma device, in this case toroidal, but it's true also for the linear one, enable quantitative model validation for intermediate transport, in this case, in H plasmas, and the related wave particle interaction phenomena. So in green is what we're going to do next. We try to work more on this control of the block dynamics with various limiter configurations. Is there something wrong with that limiter? Was it built in too complicated way, too many plates? I don't know. It's very interesting to see if you can affect the block dynamics by changing the geometry of the limiter or by applying a bias and so on. We're also measuring the electromagnetic effects associated with the blobs. It's very small probes to measure the current. In terms of the fast ion interaction with turbulence and blobs, we only had so far 2 points. So I can see some spreading. I can try to convince you it's due to turbulence, but I cannot really pin down the mechanism. So what I'm building now is a kind of a little train that goes inside the machine, and it carries the fast ion source. You have a continuous variation of the location of the source and or of the detector, which means you can really follow as a function of space, that is as a function of time, the spreading or the evolution of the fast ion beam profiles. You can see if it, if the full without maximum square goes with T or with some power of T, and is it diffusive at all or not, and so on. So this is something we are doing. The other thing we're doing is to try and move further than using probes, because we are reaching the limit in which we can't put much more probes. We're going to perturb the plasma, too significant. And we want to go smaller and smaller scales, of course, to improve this comparison. So we're trying to do it with a fast camera, both with intensifier to get more light, and gas and local gas pathing. I show a couple of examples from the intensifier. This is really work in progress. This is a movie, which is an inversion of the camera images taken toroidally. And you can see, just doing nothing but looking at the movie, that you have turbulence structures of different sizes. So this is something that it's a very good starting point. This is 50 kiloframes per second, but 190 times 140 pixels, so it's a hell of a lot of points.
So when Stuart-Zwaben does this, he can't easily match physical parameters to those because of all the ionization thresholds. And all that.
Yeah, it's
But
much more complicated. Yeah.
You have the probes, so can you help him?
Absolutely, because we can correlate with probes that are there, between the probes that are there and the light that's emitted from that same spot. So I can tell him, at least in this parameter range, what is the mechanism that emits light, and what is the mechanism that's emitting light associated with fluctuations, not just the background light, because it might not be the same. So this is something we're doing at the very moment. And this is a sort of an example of that, answering your comment. This is a conditionally sampled light emissivity profile on the left. This is the camera still on the left. So see how beautiful interchange modes we see with this from these camera images. These are what we've seen before, the same probe, the same movies, frames from probes. But using a pixel as a reference, or a probe as a reference, you can conditionally sample your movie and or the probe reconstruction, and therefore you can really measure the modes. So we can get rid of all the probes. And in fact, we did, and there is no difference. So we know there is no perturbation. But of course, you have much more pixels than probes, and so you can have a higher resolution. This is a K spectrum evolution, 2D K spectrum in time, and it's a little bit difficult to see, but this is also conditionally sampled. So at some point there's a blob going on, and you see that there are it's easier to start from the probe image. So this is the blob, these are the two modes, and then the blob tilts, if you like, the K structure, which means you're breaking the wave in a sense. So this is the K structure measured by the probe, and this is the K structure measured by the much higher resolution camera images. So you have much more K, if you like, and much smaller scale features than with the probe. So there's something, for example, for cascading and so on, I'm always worried that you can't really adequately answer with probes. So the spectrum of K and so on with probes, I'm always very skeptical about, because your limitation in resolution is fairly severe.
How much variation in intensity can the camera measure?
How much?
Variation in intensity.
Dynamical range?
Yeah.
With the intensifier, it's huge. Yeah. No problem. Without intensifier, it's tough. That I didn't show this, but we have the gas path, which is what we do in the tokamak course. But we do it with a very, very local needle that we move around. It's also a little bit cumbersome, but you can do that. Except you have the needle inside, so you can worry about the needle and so on. So I prefer to use the intensifier.
You're looking along the field, or sort of along the magnetic field line here?
Yeah. These are the inverted images looking along. So we assume toroidal uniformity to invert.
Your gas puff gives you some localization toroidally.
This is not gas puff. Yeah.
Oh.
When we do gas puff, we do a localization, and we watch from different angles. What we're gonna do also, I don't have the slide here, is to do a laser-induced fluorescence, to inject a laser light, a laser beam that pumps one state, and look with a fast camera at the transition back from that state, velocity class by velocity class. So we will have kind of an image like the one we've seen today, except resolved in velocity. So that's something that should be nice if it works. So I think that concludes my talk. Thank you very much.
Questions?
Could you please go back near the beginning where you showed the kurtosis and
Sure.
data?
I know you have good ideas about it, so I look forward to hearing them. Here it is.
So a couple of questions and comments. You didn't remark on it, but maybe it's interesting for the audience. Your kurtosis versus skewness curve, a basic question is whether that actually satisfies the realizability conditions for moments. And fortunately, it does, as you know.
It's been realized inside the device.
It's been realized.
Yeah, nature seems to know it.
But then the question is, you suggested that there may be something universal about this curve, and I know why you say that. I mean, I was one of the people that pointed out the connection to the surface waves and
Yes, I know.
where the data looks very, very similar. But the question is, what classes of turbulence do you think it's universal for? Presumably not every class of turbulence. What do you think about that?
What we tried experimentally is kind of trying to answer that question. First of all, internally we debated a long time, is it completely trivial? Is it something completely trivial associated with any PDF? And the answer was, experimentally we tried to answer that by filtering the signals, okay? We take out a portion of the signal, that's the one that's dominated by interchange mode. And if we do that, data doesn't follow this curve. So at least I can say that it's certainly associated with interchange kind of waves. And in TCV, we believe that the turbulence is also at the edge, of course. It's also associated with interchange mechanisms. Now, the fact that it's quadratic, I think, is relatively even more general, because, of course, you have the quadratic nonlinearity in the fluid equation from the convective derivative. But the fact that these coefficients are always the same is an intriguing aspect.
I mean, if you look at the way, I mean, there have been several attempts to put together statistical models that give you this kind of curve. And
Yes.
I may not be totally up to date on what people have been doing, but the ones I've looked at, what goes into the models is relatively sort of extreme events or extreme nonlinearity without the benefit of any sort of random phase type approximation. And presumably not all classes of turbulence would be correctly modeled that way, but it's interesting that you've got such agreement for a variety of things. And then the final question, are you reproducing this curve from your simulations?
Yes, we don't have, not nearly as many points, but yes, the answer is yes.
And more or less, the coefficients are the same?
Yes.
That's remarkable. I mean, it's
Yes.
wonderful.
It's scary also at the same time. Again.
Well, I mean, it may say, the question is, can you work backwards from a curve like this and learn something about the underlying physics? And maybe not so much.
This is what we're trying,
because there may be more than one rather different kind of theory that will give you a similar curve.
Yeah, so I'm looking for input on this. I know Xavier and his group did the same exercise, right?
And we try to produce also.
You've seen the same curve with the same coefficients. And many machines, including stellarators, they see that on the edge.
Is there a difference when you run the code in 2D and 3D? for this kind of result? Because it would switch, I think, from interchange to resistive interchange.
I don't think so, but I don't know if we have enough points to answer. This is something we need to do more. Yeah, I'm not 100% sure.
Earlier on, you were talking about the blob generation. You made a comment, I think, that the energy was transferred from the shear flow to the blobs.
Yeah.
What was that based on? Was it something more than what you were showing here? Or?
Yes. Oh, yes. I might even have it here, although it's in a relatively obscure representation. When we look at the, let me see. Yeah, when we look at the k space representation as a function of time, so 2D k space representation, then you have a, don't look at that. Basically, the formation of a blob is a sudden tilt in the k spectrum, in a k z, k vertical versus kr spectrum. Okay, because you're breaking something, so kr suddenly becomes finite. Yeah? Now, that tilt happens over this shearing time scale linearly with time. So if you plot, if you like, the slope of the k, of the 2D k spectrum as a function of time is linear. And we have in this here, I don't have the slide here. And then you can evaluate the energy transfer from that slope based on this advection dissipation equation. So that's how we, one of the ways we say that the energy goes from the shear flow to the blob, and it never goes back from the blob to the shear flow. Yeah.
Yes, I may have missed a point on the story of momentum transport associated particles. You say that you have events carrying momentum in both directions, or one direction. In the variation of the momentum
The
transported by the delta V. Is it always a delta? Is the delta V always in the same direction?
no, it can be in both directions. You can have both blobs of momentum and holes of momentum.
And what is the mechanism for that? Or is it either a parameter? Is it the connection length to the plates, or?
We don't entirely understand that. In some cases, you have the one phase, and in the other case, you have the opposite phase. It turns out it's dictated by the sign of the vertical field, and I don't understand that. You should not. I mean, everything should be symmetric.
Somewhere you must have some kind of a Bohm condition.
We're working on the boundary condition now. In fact, we're working on something that's extended compared to Bohm with the kinetic model to better understand. I didn't show here. I just wanted to show the effect of the blobs. But even the steady state toroidal rotation profile is a mystery. And if it's a mystery in this kind of configuration, imagining a tokamak, of course, it should be very similar. Very simple. You go from, minus CS to plus CS. But it don't. It's asymmetric. So this is an open question. It might be a test bed, much simpler test bed where we have all the data for some of these rotation theories. Yeah.
In the 2D plot of the Mach number there, did you use a local sound speed to calculate it?
A local?
A local sound speed and temperature to calculate the Mach number?
Yes. It is. This is why it takes a long time, because it's calculated local in time and space. So even the temperature perturbation.
So is the perturbation in the Mach number due to the temperature perturbation or a natural velocity growth?
It's mostly due to the velocity. Yeah.